Hello there. I'd like to welcome you to the Chapter 15 study guide, Indocere, also called, of course, the Chapter 15 review. And this chapter is about plate tectonics. Plate tectonics. So I've tried to draw you a nice, beautiful world, and I thought it needed a little color, so I've drawn in the ocean. So 20 questions this time. Here we go with question number 1. So which idea actually came first? Did plate tectonics come first? Or did an idea called continental drift come first? Which one came first? And the answer is continental drift. So here is a follow-up question. Who actually came up with the idea of continental drift? As a clue, he was a German meteorologist, and his name started with an A and ended with a W. And that is Alfred Wegener. So question number 2, let's talk about the supercontinent that Alfred Wegener hypothesized existed on Earth a long time ago. What is the name of that supercontinent? Okay, that is Pangaea, starts with a P. Question number 3. So let's talk about it as evidence. What I'm going to do in the next 4 slides is present some unusual artwork, and you have to figure out what I'm drawing as far as evidence is concerned. So here you are, you're a geologist in South America, and you're looking at a rock, and you're proudly proclaiming that it's a chunk of basalt. Okay? So maybe next year, over 2,000 miles away, you travel to the continent of Africa, and you find another rock, and you again proudly proclaim it's still basalt. Okay, and this actually is not just any basalt, it's from the same lava flow as was in South America. So what evidence does that support? So this obviously is similar rock type. This is what Alfred Wegener discovered. So here's evidence number 2. This one's kind of a little vague. So you have some interesting rocks over here in South America, and maybe they're folded and all weird looking. So 2,000 miles away in Africa, you travel and you find some similar looking things, interesting things that are not normal. So what evidence does that indicate? So this is similar rock structure or similar structures. Number 3, the third evidence, you're in South America and you find an erratic, big boulder in the middle of the field. So 2,000 miles away, you again find, or perhaps find, an erratic. So you conclude what as far as evidence is concerned? Okay, this came from similar periods of glaciation. These are glacial erratics. And the final evidence is that here is a 2,000 miles that you've been traversing from year to year. And what do you notice about the coastlines here? Okay, they seem to be a good fit with one another. So, question number 4, where could Alfred Wegener not see? Where could he not see under as far as the world is concerned? And the answer is he could not see underneath the oceans. So, question number 5 is kind of a follow-up question, and it is a true-false. So, he, as far as Alfred Wegener is concerned, did he or did he not know exactly how the continents actually moved? Did he know how the continents moved? And the answer is no, because he cannot see underneath the oceans. If he could, then he would have come up with plate tectonics on his own. So from here on out, you're going to be seeing a lot of pictures. So here's the first picture in question number 6. So what type of boundary is shown, what type of crust does the North American plate hold? Does it hold continental crust, oceanic crust, or both? Okay, it holds both continental and oceanic crust. What about the Pacific plate? Same choices. Okay, the Pacific plate is mostly ocean floor. Okay, this is 6A minus B. So plate tectonics, when you think about that, is plate tectonics a hypothesis or is it a theory? Well, it's generally accepted by the wide scientific community, so it is considered a theory. And what are the 2 players of plate tectonics? Which 2 layers of the Earth are involved in moving the plates around? Okay, you have the L part of the Earth and you have the A part of the Earth. And this was taught all the way in Chapter 1. So we have, of course, the lithosphere and the asthenosphere. Okay, this is 8 minus 1. So let's talk about these plate interactions. So I'm drawing the 3 different types of plate boundaries, and your job is to name each one. So this one starts with a C, convergent, this one is a D, divergent, and this one is T. That's transform. Okay, so I'm using a picture now from our chapter 11, I believe, or 12. This is deserts. And right here, this is just a brute memorization type of question. Do you remember what boundary is here? Would this be convergent, divergent, or transform? Okay, that's a convergent plate boundary. And what about in this location here? Okay, that's divergent along the famous video game in California. That is a transform boundary. So question number 9, I'm bringing you to the Pacific. And this whole plate, can you name the plate? Well, that's obviously the Pacific plate. What are these big cone-looking things that are completely submerged in the deep water? What are they called? Okay, these are underwater volcanoes, which are called seamounts. Okay, same picture, different types of questions here. So this area that I've indicated is where one plate is diving beneath the other, so those are called S zones. They are subduction zones. Okay, what is the deepest part of the oceans called that are very, very flat? Okay, those are abyssal plains, and these questions that I'm asking now really belong in chapter 16, but I guess I'm assuming that maybe you've learned them, I don't know. So what is this boundary here that's pulling apart? Okay, that's a divergent plate boundary, but since it's in the middle of the water, what do you specifically call it? Okay, this is a mid-ocean ridge. And along this mid-ocean ridge, you have these types of interactions where you have crusts that are sliding past one another, and these are transform faults. So question number 10 has a unique picture. So your first job is to tell me the different, what's a boundary type? And your choices are divergent, convergent, or transform. So what boundary type is shown? Okay, this is a divergent plate boundary. Specifically, what would you call this area? Okay, this is a mid-ocean ridge found in pretty much every ocean in the world. Now we're going to get a little bit more specific with this picture. What is a predominant rock type that the ocean floor is made of? And that is basalt. Okay, question number 11, a different picture and different questions, but kind of. Give me the boundary type shown, please. And there are no choices on this one. Okay, again we have a divergent plate boundary. But this is happening on land, so then you're going to call it not a mid-ocean ridge, but a rift. Now, what rock type is predominant here that makes up the large chunk of the crust? Okay, this is granite. Now, we're going to get a little bit specific here. Do you see evidence of any faulting? Are there faults here? And if so, what type of fault is there? And to answer that question, if you've been taught chapter 17, you want to look at the relative motion arrows on each side of that rift. And the answer is these are normal faults. Specifically, that's called a graben. Okay, question number 12 is kind of a generic, but we have one thing that looks like it's diving underneath another thing. So what is the name of this big boundary? Okay, that's convergent. Specifically, what type of convergent? This is oceanic continental or continental oceanic. And I guess I'm putting that here, oceanic to continental or continental to oceanic collision. Okay, what is a common name for this area of the world where one plate dives underneath the other? So again, we're visited by an old friend. This is the S zone, also called subduction. So same deal. What type of boundary is shown, please? Convergent. Specifically, it's the same deal. It's oceanic continental or continental oceanic. So this is a line of volcanoes that's formed on land. So what do you call that? This is a continental volcanic arc. And do you see evidence of a trench in this picture? The answer is yes, because anytime you have subduction, you're going to have a trench. So question number 14 now with a different picture. What type of boundary? This is convergent. Specifically, this is oceanic to oceanic. Okay, what do you call this area where you have a line of volcanoes in the water? This is called a VIA, or a volcanic island arc. Okay, what is a prevalent type of volcano that's going to be here in the middle of the water? So those are shield cones. Basalt subducts and melts and mixes with more basalt to form a basaltic volcano, which is called a shield cone. So boundary in this picture. Convergent, specifically. This is continental collision. Okay, are you likely to find a lot of contact metamorphism or a lot of regional metamorphism if you have two continents that are colliding? Okay, the answer is you're going to find a significant amount of regional metamorphism, not to say that you can't find contact metamorphism. Do you think there's thrust faults in this zone? And the answer is yes, there's plenty. Question number 16, two pictures for your consideration. One is a transform fault, the other is a transform boundary. Which one is the top one? Okay, that is a transform fault, and the bottom one is obviously a transform boundary because it's two plates sliding past one another as opposed to a segment of a plate sliding past one another. Okay, question number 17 is one of my own pictures, obviously. So welcome to Hawaii, and let's do the basics. What is all this red hot stuff that's coming up from below? Okay, that's red hot magma that's creating a volcano. And what type of volcano is it creating? This is a shield cone. And this whole setup where you have magma that's coming into the middle of the plate is called a blank blank. That is a hot spot. Okay, question number 18. It's a little bit different concept now. Okay, ancient magnetism. Magnetism, a record of the Earth's past magnetic fields, is called by what other single word or fancier name? It starts with a P. Okay, this is paleomagnetism. What does paleomagnetism prove? Well, this proves that the plates are pulling apart at about the same rate from one another. Okay, question number 19 now out of 20, so we're almost done. What mechanism drives the plates to move? What force inside the Earth is actually causing these plates to move? And let me help you out a little bit. The answer is M-A-N. Is it man? Mantle CO something. Mantle convection. Okay, the mantle is convecting or it's on the move. So when you consider mantle convection, what are the number of different ideas that scientists have come up with for convection? So how many did we talk about in class? Okay, the answer is two theories for mantle convection. The first one is called layering at 660 or layering at 660 kilometers. And do you remember the other one? Okay, this is whole mantle convection. Whole mantle convection. So there are some places where it looks like the whole mantle is convecting, other places where it could be layered. And the final question, number 20, is about VLBI. What does that stand for? The V stands for very long baseline interferometry. This is a way of watching the plates move from a satellite. And with that, this concludes the Chapter 15 study guide.